Yeah, it's in there.
All right.
And like I said, momentum should be in the title. Conservation of momentum.
Okay.
And he does 2 air card experiments.
Work, kinetic energy, potential energy, gravitation, conserved forces. That's got the pendulum in it. That's the popular one where he's standing in front of the pendulum.
Oh yeah, that's the first one.
That's not the one?
Yeah,
okay.
That's a show one.
Let's see. Lecture 15, momentum, conservation of momentum.
There you go. There you go.
So that's a 52-minute video. So it's going to be,
right.
we need to find the right part.
If you can slide through it, you'll see there's a point where he shows the air track, and he's doing an air track experiment.
All right. Well, let's get it up here.
It's like at about 15 minutes in. And then he does the same experiment a little differently with Velcro in the last half of the video, and it's even funnier.
All right. So now we're looking for the measurements that you spoke of, right? Because you're talking about the measurements that were done in the experiment, right? I just want to make sure that we know. I just want to make sure we know what we're looking for here, right?
The fact that you think I'm lying is just ridiculous. But yes,
no, I think you're misunderstanding, Gary.
Let's do this experiment. It's done.
Gary, you are misunderstanding. I don't think you're lying.
Routinely.
All right.
Yeah. So there you go. It's pretty close. A little further on.
All right, hold on. I think the audio is. I have to make sure the audio is going correctly.
He actually does the line, where he says, "Nature can deal with kinetic energy one way or the other, but nature can't finagle momentum."
And 2 cars hit each other, and
Are you hearing that?
Yeah.
Yes.
Okay.
compare the situation just before the collision with just after the collision. Here are the 2 cars, and one has a speed in this direction, the other has a speed in this direction.
So we want the one where they're going, one of them's hitting a car that's not moving. This is the wrong example. So go to, try to move on to the experiment itself, the air track.
Can we have in a collision an increase of kinetic energy? Well, it depends on how you define the word collision. The answer is yes. And in fact, I will show you an example and even do a demonstration. In the most simple case that I can think of, I have here a block which has a certain mass m. But there is an explosive inside. And all of a sudden it goes boom! It explodes. Well, before the speed is 0, and so the momentum is 0. And there comes the bang, and one piece flies in this direction.
I would move forward, see if you can find
velocity. V.
All right, not this.
You might have to go backwards, actually. You might have missed it.
So you're saying it's on the air track. So there's spring.
There's the air track. You just passed the air track. You just passed there. There's the air track. So go back forward a little more so you can see the air track right there. So there's one in the beginning and there's one at the end. So this one might be it. So go ahead and play this.
One car. And notice how frictionless it goes when I touch it.
Skip ahead a little bit because the two mass will be the next experiment.
223, 219 milliseconds. That is well within the uncertainties.
Right, so that's just
what was the number?
One mass cars pushed away with a spring. So we have the same amount of momentum on both sides, both the same velocity. So that's pretty obvious.
Whereby I'm going to make M2 twice the mass. M2 is 488 plus or minus 1 gram. Now that's going to be interesting because now you really begin to test the conservation of momentum. The momentum before is 0. I burn the wire, momentum afterwards is also 0.
Can I ask you to pause this once in a while?
The velocities, oh, I erased this. V2 prime divided by V1 prime equals M1 divided by M2. And so twice the mass will get half the speed. And so now you're going to see that one car will go twice as slow as the other. That's the only way that nature can conserve momentum. Nature has no choice. Nature can deal with kinetic energy one way or another, but it cannot finagle momentum. So it must give the more massive car half the speed than it gives the other car. And so we're going to redo this experiment now with a car here, which is twice the mass, and this one is one's mass. So this is the 244, and the one on your right is the 488.
So just pause for a second. All right, this isn't the one where he bangs it into the cart. This is the one where the spring pushes them apart. So this is essentially illustrating the gun in the sense that we have a heavy mass and a light mass, and it's going to demonstrate that the momentum will be conserved, but the kinetic energy won't be.
Yeah, so this will go right to your claim that the mouse and the elephant will both have the same velocity after being pushed by a spring, right?
No, I said they'll have the same velocity if I take their weight and have that as the compression of the spring. So the compression for the elephant will be huge.
Oh,
the compression for the mouse.
You left off the proportional larger spring.
I didn't leave it out.
Okay,
I showed the actual scale on the camera.
Yeah, you didn't show two scales. You showed one scale that has the same amount of spring.
I showed the scale, and I showed compressing it a lot and compressing it a little. I said I put the elephant on, it compresses a lot. I put the mouse on, it compresses a little. I did those exact words.
Okay, so you did demonstrate conservation of all these things that we say that is conserved. Cool. All right, well, let's finish watching this little one here.
Bring them together again.
This isn't the free momentum experiment.
So I do the work now. I always do the work here in 26100. I do the work. I squeeze these springs. I get paid for that, by the way. And that's potential energy if it goes into the spring. There it is. Momentum is 0. Kinetic energy is 0. I have to zero the timers. Oh, and I would like to make a prediction. I would like to see, we'll measure T1, and then we'll measure T2, and then we get a number, and we get a number, and if we multiply this number by 2.00, then I would like to get this number within the uncertainties of the measurements. There is always an uncertainty in any measurement that you do. All right? Make sure that are the timer 0? Okay, there we go.
So exactly what you'd expect. The twice as heavy goes one half the velocity, the one half the mass goes.
Everything that we say is right. Awesome. Okay, what was let's conservation of momentum is the first one here. Let's see.
Yeah, this is the wrong video. This one isn't going to show the collision, so you have to go to the next video or the one before this.
But the point I would make here is that you completely misinterpreted what he's saying. He is clearly making a distinction between energy and momentum, and he's clearly making a distinction between different forms of energy, the potential energy of the coiled spring, for instance, and he's clearly making the point that energy is a distinct.
I'm sorry. He's clearly pointing out that momentum is conserved, and that he said it overtly. Nobody, and at any point in any of these discussions has tried to claim that momentum isn't conserved. Your argument is that energy just doesn't exist or isn't a thing, or that energy is
it is whatever he wants it to be.
Momentum. Yeah. That's not my argument.
Momentum is not the same as energy, sir.
You can keep saying it. There is no such thing as whatever energy is outside of the context of velocity. Mass and velocity is energy.
The professor that you've been quoting all day clearly disagrees with you because he has made several references to energy in these presentations so far. So he clearly believes that energy is a meaningful physical concept in complete disagreement with you. So you can't use his presentations that completely disagree with you to support your nonsense.
That didn't happen. That didn't happen.
Yes, it did. Did he not reference kinetic energy? You quoted
he certainly did,
referencing kinetic energy.
He's doing the next experiment right here where he's going to bang the one mass cart in the two mass cart, and he's going to create extra momentum in the same direction.
No,
So
he's
there's
not.
almost no
Yes,
heat
he is.
that is
so
generated in the springs during
All
the
right.
collision.
Let's see what he says here.
Reasonable approximation
Pause for a minute.
No.
Let me just explain
an
something.
elastic
because I-
collision. But of course,
No.
there's always air
We're going to
drag.
watch
I
the
can never
experiment
take
and
air
then we're
drag
going
out.
to-
I don't
So there's
understand. I
always
can't.
some external
I've
external
only
force
watched
on the
this clip
system.
100
So
times. I
momentum
have
is
video
never
of it.
exactly
Then shut up while I'm
and
watching
kinetic
it.
energy is never exactly conserved either. So it's only an approximation. So I have one mass of unit 1, I will tell you what that is, and I bang that into number 2. And the masses that I have, one mass is 241 plus or minus 1 gram, and the other mass that I have is 482 plus or minus 1 gram. And I have 2 of these, and in my first experiment, I will use these 2. So this is the ratio that you see, 1 to 1. I will give it a certain velocity, which I cannot tell you what that is. That depends on how happy I feel. If I push hard, then the velocity will be high. If I push softly, the velocity will be low. But it is something. And then we're going to get here V1 prime, and there is a prediction that this velocity will be 0. Look all the way on the blackboard there. You will see if the masses are the same, and there's an elastic collision, this one will stand still, and this one, V2 prime, will have a velocity V1. So that's a prediction. The second case, I bounce one car onto another one which is twice the mass, certain velocity, which I don't know what it is, and now what are we going to get? So mass M1 is half the mass of M2. So this is a 1, and this is a 2, and this is 3. 1 minus 2 is minus 1, divided by 3 is minus 1/3.
Pause here, pause.
So number 1 comes back.
Pause.
So what he's done here is he is simultaneously solving for conservation of kinetic energy and conservation of momentum. That's exactly how he got this formula, right? You can see it there on the board. You can see it on the board, can you not, sir? Can you see that on the board?
I have 50 videos showing this clip.
Can you see that on the board here, sir?
I'm not going to play your games, okay? I'm going to stay.
Okay, Toon, can you see on the board that he is simultaneously solving for conservation of momentum and conservation of energy?
I do see that.
He's made the
Okay.
two formulas equal.
Does it follow then that that Professor Lewin agrees that energy is not a physically meaningful concept? It follows that he does not believe that. So you're using this guy's presentations to support this argument is completely mendacious and utterly delusional, sir. This guy clearly doesn't agree with you, and he's about to experimentally show that you're wrong.
I would just like you to look at the carts, okay? So wait till he puts the carts, the 2-to-1
no.
carts.
This is your assertion, Gary, is that the theory and the practice don't match. And here he's showing the theory.
Is that this experiment will be demonstrated to be a farce in the first place. And in the second place, if it was actually true, he's saying I can create free momentum by just hitting a heavier object. So anytime I hit a heavier object, I will create some amount of free momentum.
All right. Well, Tony,
That's not what he's going to say. But you're completely.
Play it. You'll make the free. He's going to do it right in front of you.
If you bounce a lighter object off a more massive object, no surprise that it bounces back. So that's minus 1/3. And when we look here, we have 2 times 1 divided by 1 plus 2 is 3. That is plus 2/3. So number 1 will come back with a speed 1/3, which of course, since this is sign sensitive, we get 1/3 V1. And this one is plus 2/3 V1. That's the prediction.
1/2.
And the way we're going to measure it is by measure the time for the objects to move over a distance of 10 centimeters. No matter how long you see these cars to be, there is here a piece of metal which is 10 centimeters long. It goes through a slot with a diode. We have one system here and one there. And during this 10 centimeter movement, we measure the time. We begin when this piece of metal enters the diode system, and we stop the time when it leaves the diode system. And each one of those cars has this 10 centimeter metal plate. So the way we're going to do this is by measure timing, of course. This velocity will give me a certain time, and this velocity will give me a certain time. Whatever comes out, you will see that on this timer. Then T1 prime is, in this case, it stands still, so must be 0. And T2 prime,
because we agree
must
on
be
what
the same as
happens with
T1.
1 on 1. We want to see
So these two numbers you should be able to compare directly. What kind of uncertainties do we have? It's hard to tell. But I would say, as I argued last time, that you should allow for at least about 2.5% uncertainty in each time. If it comes out better, then you're lucky. If it comes out worse, then it is a bad day. 2.5%, and I argued last time how I reasoned about the 2.5%. Now we do this experiment, we get a certain T1. And so this one goes back with 1/3 of the speed, so it will take 3 times longer to go 10 centimeters. So I'm going to multiply this time by 1/3, and whatever comes out should be the same as this. So let me move this up a little. T2 prime. The speed here, the forward speed, is 2/3, so it will go slower. So if I multiply this time by 2/3, then I should be able to compare it with T1. And all of that, all these times, I think, will not be any better than roughly 2.5%, except if we are a little lucky. Okay, system is up, timers are up, timers are up. This will be the time T1. This will be the time T2 prime. And this is the one when the object bounces back. So this is T1 prime. You won't see that it is negative. It will go back through the same slot. And the electronics is arranged in such a way that when it goes back through the same slot, that it will initiate this timer. I will zero them. First you have to tell me whether they are working. I will just let it go through this slot. This one working. Tell me that this one is working. If I send this one back, this one working. Okay. Okay. There we go. This is the one that will have no speed, and this is the one that we're going to give a velocity. You ready? I hope you know what you're going to see. This one will come to a halt, and this one will go on. They have same mass. There we go. This one is indeed coming to a halt, and this one took over the speed. What are the numbers? 194 and 196. Only 2 milliseconds difference. That is an incredible result. 0.194 and 0.196. It's only 1% difference between them. Way within my wildest expectations. Because my expectations were that they could be off each by 2.5%. Now we go to the 1 to 2. So here is the car which has twice the mass. It's important that I zero it. And now this one is going to come back.
Pause here really
So you're
quick.
going to see this one come in, give you the time here.
You see the close-up.
This one goes through here, gives you.
Why do you want to pause?
I want you to see the cart, so you'll be able to see both carts in the image, okay, with a close-up, and I want you to look at the cart.
here, this one will come back, gives you the time here. Are they 0?
There.
Okay.
Pause.
You ready?
Pause.
Yeah.
Pause. No, you won't do it. Okay.
There we go. Okay. Now comes the real acid test. 1, 2, 3, 1, 8, 6. 1, 2, 3. And what is the last one? 3, 7, 5.
All right, so let's go back. What you wanted to pause? Why?
There, right there. Okay. Well, I'm just saying that the theory. See the lump of clay on the cart. Okay,
Yeah.
first. All right. Now it's one on each side because the carts have to be balanced. And look at the little black thing there. That's a weight. Okay, and there's one weight on the small car, and there's one weight on the one that's supposed to weigh twice as much. So obviously the aluminum is cut to lengths of 1, 2, 3, 4. You can buy them that way. So they're obviously not the weights that he claims. The 2-mass cart clearly doesn't have 4 weights on it. You know, it doesn't have 2 that you can see.
Why is it obvious that the entire cart has a different mass than what he claimed?
I just told you why.
No, you didn't.
Right,
you made a baseless religious assertion.
Okay, let me just say, do you recognize that they would cut the carts in lengths that would be proportional?
Do you think you can, have you measured the lengths of these carts? Do you think you can?
Yeah,
with what accuracy?
Yeah,
With
obviously,
what accuracy?
obviously, Gary is just making up stuff here because he has to. He has
You
to.
don't want to hear the argument. Clearly, you don't want to hear the argument.
No, we don't want to hear you lie about stuff, Gary.
Okay, I didn't lie. All right, I didn't lie about a damn thing. Calling me a liar is lame. I didn't lie about anything.
You came in claiming that this evidence would substantiate your position, and instead, this evidence is actually completely debunking you, is validating what I explained to you earlier.
It's free momentum. So finish it then. Finish it, and it proves that it creates free momentum. This is the momentum equation.
It doesn't, sir. It doesn't. No, it doesn't.
All right. We'll just let Gary seethe a bit there.
And let me use my calculator. 375 divided by 3. I could have done that by heart, of course. This is 0.125. An amazing agreement. Amazing. Only 2% off, less than 2%. Now here, 0.186 times 2 divided by 3, 0.124. I can't believe it.
Wow.
Less than 1% off. So you see in front of your eyes that we were able to create something that was indeed extremely close to elastic collisions, in spite of all the problems that we have air drag, and that, of course, there's always some loss.
All right. So Gary, here you go. I'll just put this up right now. Right there. We've got this right here. Right here. Just there you go. Oh, sorry. Let me go back to this. All right. So Tony, Gary, go ahead.
All right. So the clear conclusion is that 100 momentums went in, 133 went away with the cart going this way, and 33 went this way. In my opinion,
the total momentum is conserved.
Yeah.
Well, in my opinion, this is what you had. You started with just one object moving with 100, and now you have 2 objects in the universe moving with a total of 166.
Oh my gosh!
So, in my opinion, that's.
Oh my gosh!
You don't understand how. Then you don't understand how vectors work.
I don't understand how energy cancels. Yes, I don't believe energy ever cancels. It never happens.
Hilarious.
So we're back to the pendulum argument. So let's do the pendulum example of this exact experiment. So
No,
here's
you-
the pendulum
No, no, no.
example.
Gary,
This is babbling nonsense.
Gary,
No,
you,
sorry,
you,
this is
your
legitimate.
own
You're
citation
deranged, sir.
100%
You're deranged,
destroyed you, Gary.
Okay, so
You don't see
won't
that.
let me finish, right?
It's
You won't let me
embarrassing.
finish, right?
This
you won't
is
let me finish?
Gary. This is like
you won't
this
let
is
me
like. Hold
finish.
on, Gary. I want to
That's
say
what we know.
this is like in that portion, that movie, A Few Good Men, where you know he's up on the stand and he says a bunch of stuff that incriminates himself, and Tom Cruise.
This is like the
and-
Catholic Church, the
and
minister
Tom
making
Cruise, hold on.
rationalizations for nonsense. Okay, you've lost
and,
the argument.
and Tom Cruise says,
You're pretending you won.
all right, hold on. Just let me finish talking. All right. And Tom Cruise says, you know, basically he's like, he totally just screwed himself. Give him a little grace, get him off the stand. He has rights. And that's what has happened right here, right now in front of everybody, Gary.
Right. I
You
phoned
have
numerous
demonstrated
I phoned
perfectly
you.
that you do not understand this topic and that your own citation destroyed your
You're a
claims.
failure of a human
I
being,
just
sir.
proved you.
You can't handle the truth.
Free energy nonsense. Free energy
wasting your life
believers.
on a delusional,
100
on a
goes in,
delusional
150
fantasy.
comes out, then the two things crash, it disappears, then you make it again, then you disappear, then it makes it again, then it disappears, you make it again, it disappears.
You're just babbling,
It's a
sir. You're
nonsense
just babbling.
theory. You are pwned.
You're just babbling absolute
No,
nonsense.
you're an
Nobody
idiot.
knows what they're
You're
talking.
an
Nobody
idiot.
who,
You're an
nobody
idiot
who.
too. I call you first. Okay, I remember your glue, whatever the bullshit is.
You were just shown to be wrong by direct experiment, sir. And this was something that you introduced as evidence because you're that
right. And I'll reassert my point that I can show that he faked the experiment.
You can't show anything of the
Okay.
sort, sir.
Well,
You're a
I'm
liar
saying
and a fraud.
All you have to do is look
Anyway,
at the cards.
I need to go.
Law
I'll
of
talk to you
play
later.
doesn't
All right, thanks,
lie.
Tony. All right, so here's momentum, the conservational momentum, right here in a closed system, the one that doesn't exchange with any surroundings. The total momentum remains consistent. This fact is known as the law.
Cancel
The law of
momentum is
conservational
ludicrous.
momentum is implied
You
by
have no
Newton's laws of
experimental
motion. You just watched it. Suppose, for example, that two particles interact as explained by the third law. All right,
Same
hold on.
experiment.
Just a second. As explained by the third law, the forces between them are equal in magnitude but opposite in direction. If the particles are numbered 1 and 2, the second law states that F1 equals dP1
whatever.
over dt,
You're gonna just
and
keep
F2
muting me
equals
and we're gonna end
dP2
this.
over dt. Therefore, dP1 over dt equals negative, and that's what you ignored, dP2 over dt.
No, I didn't ignore anything.
So that's
These are
what you did, Gary.
irrelevant, no evidence. You people
we
are
just
pathetic
literally watched the
liars.
evidence
You're
happen.
such pathetic liars. You wouldn't even let me explain why his experiment was flawed. It had clear flaws in it, a mechanical flaw. All right, the weights couldn't be what he claimed them to be. It's impossible if you
Well,
look at the cards.
then you have the burden of proof to reproduce the
I
experiment.
just demonstrated. You wouldn't even listen to the burden of proof.
No, you made claims. You made blind faith
I made
religious
obvious
claims.
Visual
Blind faith.
claims. Yes, they're
Blind
visual.
faith.
You can
Absolutely.
see
Your religion is making lies about Walter
Okay, I
Lewis'
didn't lie
experiment.
about anything.
So
I never
go
lied.
reproduce
You're a
that
liar to call me
experiment
a
yourself.
liar. Okay, I never lied.
Go reproduce. You obviously. I mean, there's hundreds of people that just watched you lie about it right here,
I
right
never
in front of
lied.
everybody. Well,
Okay,
then
you're a liar.
prove.
You're a liar.
Yeah,
I never
got
lied
it.
about anything.
Prove that he lied. I mean, you're asserting that he lied, so you're going to have to prove that he did that by
You wouldn't let me. You
going
wouldn't
and
let me.
getting it.
You wouldn't let me.
No.
The proof is visual. You
no,
can see.
no,
the
it's
proof.
not. No, it's
Yes,
not.
it is.
He has
The
masses
card
on
has
there.
Things attached to it. You can see what's
Yes,
attached to the card.
and that's obviously done so that they're the same multiples of masses.
I'm sorry. There's
that's
no
called a
evidence of
controlling
that. There is
controlling
no
for a
evidence that
confounding
it's
variable.
twice as heavy. The evidence doesn't work. It doesn't make any sense. You can't. If you're going to make it twice as heavy,
So-
you have to have twice as many extra things added to it. And instead of twice as many, there's half
you
as
would
much.
have what you do is you would go measure the mass of one and measure the mass of the other and say,
We
oh
didn't do
look.
that. He didn't do that.
Well, he didn't do it on camera.
That's right.
Of course,
didn't do
yes.
it on camera. That's
Yeah,
right.
he
because
doesn't-
The
he
experiment
doesn't-
didn't work.
Yeah,
The
all right.
experiment didn't work,
All right.
and that's why he had to
All
fudge
right.
the masses.
All right, crybaby Gary. All right, tell you what,
You're
Gary.
a liar,
Thanks.
fucker.
Thanks for coming, Gary. You've been a horrible person.
You're a suck. You're a piece of fucking lying suck.
There's a reason why nobody wants to debate you because
you're cowards. You show right in this debate why you're a coward. You didn't show a single piece of physical evidence, not one. You claim guns don't
I
have
didn't need to, Gary.
Momentum. You made outrageously idiotic claims.
You provided the evidence contradicting your claims. I didn't have to.
Didn't do any
You did
such
that.
thing,
The first law of Flurf was proven again. So, Gary, thanks a lot.
Moron, you fucking dupe.
Anything you'd like to say on your way out, Gary?
Yeah, get what you deserve, fucker. You're a menace to science. You and your cartoon channel. You're a fucking menace to logic, reasoning, science, dignity. You are an insult to the human fucking race.
Man, the projection is heavy, dude. All right, thanks a lot, Gary.
Get
Bye,
what
Gary.
you deserve. Get what you deserve.
Bye, Gary. The
lying piece of shit.
bottom right is the exit button on the